in the Beginning by Dr. Walt Brown, Liquefaction During the Flood on page 206 on a flip book that you can get at creationsciencecenter.org. Liquefaction During the Flood. The flooded Earth had enormous unimpeded waves, not normal waves, but waves on top of and generated by fluttering hydroplates, which with each flutter cycle, water was forced down into and up out of the accumulating sediments on the seafloor. Under a wave peak, water was forced not only down into the sediments below, but laterally through the sediments toward pressure minimums that were simultaneously occurring 1/2 wavelength away under wave troughs. Later, when a wave trough arrived, the flows reversed. The water flowed upward. Water almost completely surrounded each sediment particle deposited on the ocean floor during the flood, giving each particle maximum buoyancy. Therefore, the sediments were loosely packed and held much water. Half the time during the flood phase, water was pushed down into the sediments stored for the other discharge half cycle, in which water flowed upward. During discharge, liquefaction occurred if the water's upward velocity exceeded a specific minimum. When it did, interesting things happened. A thick horizontal layer of sediment provides high resistance to upward flowing water because the water must flow through tiny twisting channels between particles. Great pressure is needed to force water up through such layers. During liquefaction, falling sediments and high waves provide this high pressure. If water flows up through a bed of sediment with enough velocity, water pressure will lift and support each sedimentary particle. Instead of thinking of water flowing up through the sediments, think of the sediments falling down through a very long column of water. Slight differences in density, size, or shape of adjacent particles will cause them to fall at slightly different speeds. Their relative positions will change until the water's velocity drops below a certain value, or until nearly identical particles are adjacent to each other, so they fall at the same speed. This sorting produces the sharply defined layering seen in sedimentary rocks worldwide. As you will see, these vast, sharply defined sedimentary layers are unmistakable characteristics of liquefaction and a global flood. Such sorting also explains why sudden local floods sometimes produce horizontal strata on a small scale. Liquefaction can occur as mud settles through water as water is forced up through mud. To understand liquefaction better, I built the simple apparatus shown in figure 105. Right there's the 105. The 10-foot-long metal beam pivoted like a teeter-totter from the top of the four-legged stand. Suspended from each end of the beam was a 5-gallon container, one containing sand and one containing a mixture of different sediments. A 10-foot-long pipe connected the mouths of the two containers. Gently tipping the metal beam raises the water tank. Water flowed down through the pipe and up through the bed of mixed sediments in the other tank. If the flow velocity exceeded a very low threshold, the sediment swelled slightly as liquefaction began. Buried objects with the density of a dead animal or plant floated to the top of the tank. Once water started to overflow the sediment tank, the beam had to be tipped so the water flowed back into the water tank. After repeating this cycle for 10 or 15 minutes, the mixture of the sediments became visibly layered. The more cycles, the sharper the boundaries between sedimentary layers. Water hammers. Water hammers occur usually with a loud bang when water or any liquid or gas flowing in a pipe is suddenly stopped or slowed by closing or narrowing a valve, such as a faucet. A water hammer is similar to the collision of a long train. The faster and more massive the flowing volume of water, the greater the sudden compression or pressure pulse throughout the pipes as the water is slowed or stopped. A water hammer concentrates energy just as a hammer striking a nail concentrates energy and produces forces many times greater than a resting hammer. Flutter. Vibrations often begin when a fluid or liquid or gas flows along a relatively thin, flexible surface, such as the wing of an airplane. a reed in a musical instrument, or a flat plate. If A, the flowing liquid, continually thumps or pushes the vibrating surface back down toward its neutral position, and B, the thumping frequency approaches any natural frequency of the flexible surface, large damaging oscillations or renaissances called flutter can occur. Both the area of the Earth's crust, 200 million square miles, and its squishy supercritical water foundation gave the crust great flexibility. Therefore, flutter quickly began as water was escaping beneath Earth's crust during the flood. Each narrowing of the subsurface flow channel by the vibrating crust slowed trillions of tons of water and produced water hammers that thumped the crust at each of its natural frequencies. Undulations rippled through the crust, causing other water hammers, more undulations, large flutter amplitudes, and pulsations in the fountains of the great deep. Most people have heard water pipes banging or have seen pipes burst when only a few cubic feet of water were slowed. Imagine the excruciating pressure from rapidly slowing a moving underground ocean. The escaping subterranean water produced another chain reaction. Pillars, on figure 57 on page 134, had to carry more and more of the crust weight because the diminishing subterranean water carried less. Therefore, pillars nearest the rupture collapsed first, but in stages. Then adjacent pillars suddenly supporting additional loads also began collapsing in stages as a falling house of cards creates more vibrations. The crust vibrated in complex wave-like patterns like a fluttering flag held horizontally in a strong wind. Vibrations closed valves, which in turn created water hammers, which created more vibrations. Amplitudes grew and waves ripped around the earth. Forces similar to us will not compress water much. Forces familiar to us will not compress water much. However, the weight of 60 miles of rock will compress liquid water by about 34%. Because the supercritical water trapped below the massive vibrating crust was primarily a gas, supercritical water was more than 1,000 times more compressible or springy than liquid water. The supercritical water acted as trillions of long, soft springs supporting a massive, high inertia crust. That combination, a large mass vibrating on a very compressible spring, produced huge amplitudes and long vibrational periods about 30 minutes in length. Understanding the flutter will become extremely important when we get to the origin of Earth's radioactivity on pages 387 to 441. For example, see figure 213 on page 399. This chapter will explain basic errors in radiometric dating, the staggering energy and power of fountains of the great deep, and why flutter amplitudes were even greater than is now apparent, large enough to cyclically lift the top of the fluttering crust out of the flood water.